the floor to Dr. Kuksenko from Institute of Chemistry of Surface, named after Chuiko, National Academy of Science of Ukraine.
Тепер буде презентація пана Куксенко.
The subject of our report
Тема
is
нашого
non-porous three-dimensional
доповіді – це безпористий наноструктурований 3D кремній для анодів літій-іонних акумуляторів. Історія зоряних батарей, які отримують електричну енергію як хімічну енергію, почалося з створення свинцевої батареї в 58-му. І ось тут показаний графік історії зоряних батарей.
Lithium-ion batteries provided an energy density of about 70 watt-hour per kilogram. And today the energy figure has been more than tripled owing to optimized electrode materials and design engineering. The lithium-ion battery market is entering into the second rapid growth phase, which is driven by emerging applications such as large-scale electric vehicles and energy storage systems. The predicted market expansion of lithium-ion batteries from 2010 to 2020 is surprising, with a tenfold growth from approximately 12 billion United States dollar to 120 billion United States dollar. More than 80% of lithium-ion batteries market at 2020 is predicted to be occupied by two emerging application sectors. Those are energy storage systems and large-scale electric vehicles. Energy storage systems sector weighs about 54% of total market size at 2020, while the size of large-scale electric vehicle sector is a half of energy storage systems market share. With this perspective, electrode material will play a major role in the next generation battery design. Manufacturing technology of lithium-ion batteries is very simple. These devices consist of two electrodes in the form of thin layers on the copper and aluminum foils, and wet aprotic electrolyte separated between them. The main cell reactions in lithium-ion batteries are reversible lithium-ion incorporation extraction in charge-discharge cycles between two insertion compounds. With such a simple technology, a problem of large-scale production rests not in technology but in science. As promising materials for the positive electrode considered stable in air lithiated layered oxides, fluorophosphates, silicates, and structurally integrated composites. As promising material for the negative electrode considered silicon. Readily available and low-cost silicon is considered as alternative for the conventional graphite anode because of its high capacity for lithium-ion storage, nearly tenfold higher than that of graphite. On replacement graphite anode by silicon-containing anode is possible to enhance the energy density of lithium-ion batteries with traditional lithium cobalt oxide cathode by up to 40%, and with new lithiated nickel cobalt aluminum cathode up to 70%. Using nanosilicon leads to better cyclability than in the case of microparticles. To improve the structural stability of the electrodes around the silicon particles, usually create a space that is filled up with swelling alloy. Such strategy does not seem promising for practical use because of low loading capacity of the suggested electrodes and low Coulombic efficiencies of the cycles due to renewing contact of the active surface of the swelling lithium silicon alloy with electrolyte. With the aim to reach the acceptable values of accumulated irreversible capacity at high capacity loading, we propose a new nanocomposite configuration wherein the silicon nanoparticles deposited on a conformal coating from graphene layers interconnected together through a thinning heteroatoms, which gives them mechanical strength. Such coating is highly conducting and electrochemically active with respect to incorporation and release of large amounts of lithium. With this new nanomaterial, it is possible to control the strain of the lithium silicon alloy, thus preventing its contact with electrolyte and to fabricate high-density silicon-containing electrodes. So this technology creates non-porous three-dimensional silicon graphite heterostructures called as three-dimensional silicon as new anode materials for lithium-ion batteries. In addition, we were the first to use fluoroethylene carbonate-based electrolytes instead of ethylene carbonate. Ethylene carbonate was totally replaced by fluoroethylene carbonate. The three-dimensional silicon electrode cycling parameters achieved loading capacity more than tripled compared to graphite anodes, and accumulated irreversible capacity equals only 1/4 of reversible capacity are due to high density of the electrodes and formation of stable electrode-electrolyte interface. One can see a comparing of our results with the best results that published by our competitors. After the appearance of our publications in 2010 devoted to the effectiveness of electrolytes based on fluoroethylene carbonate, the necessity in fluoroethylene carbonate on the market has increased dramatically. Our silicon anode materials for lithium-ion batteries will provide an opportunity to sharply increase their energy density up to 400 watt-hour per kilogram, to lower the cost lower than $200 per kilowatt hour, and increase the service life up to 20 years. This will open up a potentially huge market of batteries to increase the efficiency of power generation plants and create a snowballing demand for electric car. On these figures, you see 32 megawatt lithium-ion battery packs at a wind power farm in West Virginia, and electric vehicle Tesla Model S. Currently, the Model S pack comprises up to around 7,000 Panasonic 3.1 ampere-hour cells using a lithium nickel cobalt aluminum chemistry. Using instead the anode, our anode materials will give capacity more than 4 ampere-hour. Here are our publications in English, and here are the competitors, our competitors, and thank you for your attention.
Thank you, Dr. Kuksenko. It was very interesting, especially the first slide you have commented about applications. Any questions to author? Please.
Show slide now, or this one. My remark. You say about no, don't change, but your role electrode morphology don't change after cycling. That you have not shown. Show for the beginning, after 1,000 cycles, and so on. So show one and say that no changes is not correct.
It was the same morphology at the beginning of the process and at the end.
But you have not shown this one.
Yes, yes, I saw it for this.
Is there any chance to organize a business here in Ukraine using this technology?
We propose only new material for one of two electrodes lithium-ion batteries. We propose to organize chemical production of the new material, not production of lithium-ion batteries in all.
But you know that in Dnepropetrovsk there is a big plant which produces accumulators. Maybe they may be interested in your developments.
Yes, maybe. I hope.
Did you try to get the contact with them?
I think production of components is also an important step to develop full-scale production of batteries. So if you start producing small batches of anodes or some invention you have developed through the projects, so you can succeed with these small components only. What do you think?
Okay, I hope.
Okay, no answer.